solve the problem.
What are you talking about?
Close your eyes. Pretend you're overlooking a train track. Imagine a train racing past, faster than any train you've ever seen. Now, I want you to imagine, as the train is flying past, two lightning bolts crashing beyond the tracks at the same time, 100 meters apart.
So what?
Patience. Now imagine that you're standing in the middle of the train during the exact same scenario. Would the lightning bolts be simultaneous?
Of course.
Not if light moves at one speed. Close your eyes.
Oh, but this is ridiculous.
Put yourself back on the moving train and really think about it. Do it, Michele. Now watch the lightning bolts. Were they simultaneous to you? No! Because you were moving towards one and away from the other. To me, standing still, they were simultaneous. How could the two of us experience the same event differently?
We couldn't. Unless...
It's not Maxwell who gets it between the eyes. It's Newton. What are you saying? Time is not absolute. Holy hell. I'm writing the paper, Michele.
Hey, I'm FTFE and welcome back to the channel that does the stupidity, what the Michelson-Morley Experiment did, the concept of a luminiferous ether. Thank you everyone for joining me today. This is a bit of a different stream to what you are normally used to with me. I'm not going to be going and having a heated discussion with people that don't understand the concept of tying their shoelaces. Instead, we're going to be talking with someone who is actually very, very smart. The gentleman I'm talking to today is extremely intelligent and has been assistant professor at Department of Physics and Electronics, Handraj College, University of Delhi, from 2013 to 2020, and definitely knows his stuff. I'd like to introduce you to Mr. Das. Mr. Das, hello. Thank you very much for joining me today.
Hi, thank you for inviting me, Greg.
No worries. I've broken my screen there. 1 second. There we go. Get you up on this. Thank you very much.
Hi.
Mr. Das, your videos on relativity and length contraction have helped me understand this entire discussion more than any books or anything that I've read. You have an extremely good way of explaining things, and that's why I wanted to reach out to you today and get you on. I'm
very happy to hear that.
I talk to flat earthers that don't understand the most basic things about physics, and some of them have jumped from not understanding basic physics to not understanding relativity. It doesn't really help any of their arguments, but I wanted to reach out to you and maybe have a discussion with you today about the concept of relativity and length contraction and where that came from and how it applies to us, and maybe clear up some of the misunderstandings around it. So before we get started, would you just like to take a minute or two to introduce yourself?
Sure. So my name is Dibyajyoti Das, or Mr. Das, and I am an assistant professor of physics at the Department of Physics and Electronics, and I've been teaching there since the last 10 years almost. I also have a YouTube channel, For the Love of Physics, where I mostly post lecture-style videos on physics. In fact, I have a lecture series on special theory of relativity, where I've discussed most of these concepts, the historical development of these ideas, what STR as a subject of physics is, and space-time, mostly geometries, the difference in the geometry related to Minkowski space-time. So I've posted a number of lectures on YouTube, so if anybody is interested, they can check out the channel. And I'm very happy that you have invited me to this discussion, and I'm just hoping that maybe I can bring a little bit of clarity to this kind of a discussion, and if somebody benefits from this discussion and develops a little more clarity on this particular subject of relativity as well as the historical development of these ideas, then I think my job would be done, and I'm very happy, and I'd be very happy with that.
Well, like I said to you in the pre-show, there is one particular person I was talking to who was a flat earther. We'd kind of brought him around after talking about celestial navigation, but then he got dragged into this relativity argument and it took him back. And it was your particular video on muons and how it shows time dilation and length contraction that explained these concepts to him, and it was mind-blowing for him to, the way that you explained it, it made everything click in his head. And again, that's one of the reasons that I've come out to you now.
If I can point out some,
Yep,
yeah,
please
if I
go
can
ahead.
point out something, in that video I discussed how muon particles, which are originated at the top level of the atmosphere, they come down and they decay at a particular, in a manner that is not explained by non-relativistic physics.
Yes.
In fact, the experimental validation of that experiment is how do you say, an experimental proof of relativity. In fact, the scientists who performed this experiment got the Nobel Prize in Physics for doing this particular experiment, therefore giving validity to the subject of relativity. So it's a very historically prominent and important experiment.
Yeah, and I do think that when you look into the Muon experiment, it's such a good explanation of co-moving frames versus non-co-moving frames, because you have to place yourself as though you're riding the muon, almost. Yeah. And as from the perspective of the muon, if you consider that your non-co-moving frame, then the atmosphere is the thing that is at a relativistic speed and is the thing that's contracting. But then if you view it from the atmosphere, there's a symmetry to it, and the symmetry, I think, is the most beautiful thing that I've ever experienced in physics. It's almost a mind-blowing understanding of the way the universe works.
Yes.
Yeah. So the crux of this argument kind of lies around what the Michelson-Morley experiment showed us, and the implications of that for physics afterwards. So you said that you could give us a brief introduction of the history of the Michelson-Morley experiment. I'm happy to hand over the microphone to you and let you go through that.
Yes. So if I can do it in a very simple manner, if I could give a brief introduction to the historical development of these ideas, I would like to start with what is known as the principle of relativity. So you probably already know that special theory of relativity relies upon two fundamental postulates. The first one is the principle of relativity. Now, maybe you already know that the principle of relativity was actually not given by Albert Einstein. It was given by Galileo Galilei long time back, because he was giving the principle of relativity for mechanics mostly. So what does the principle of relativity tells us? It simply tells us that the physical laws are the same for all inertial observers. So that means if we study physics and we look at the physical laws, whether you are at rest or whether somebody is moving with respect to you at a constant velocity, we will not be able to distinguish between the physical laws, right? So would you like to give me an example to bring a little clarity to the conversation?
So of relativity?
The principle of relativity, the first postulate. So if I want to disprove basically the Lorentz deformation hypothesis, I'll have to explain the principle of relativity once. So imagine that, for example, I am with a group of friends and we are playing some kind of a carom board or a billiard or pool where objects are colliding with each other, for example.
Yes.
And let's suppose we have a similar setup on a moving vehicle. Let's suppose there is an aeroplane or a flight which is traveling through the air at very, very high speeds. Let's suppose this is a very hypothetical sort of ideal sort of thought experiment, where an aeroplane is traveling at very high speeds through the air, and there is no jerking, there is no turbulence. It's moving very smoothly with constant speed, and we recreate that similar setup on the aeroplane. So let's suppose me and a couple of my friends are playing either billiards or carom board, where objects are colliding with each other, and a similar setup is on in an aeroplane, let's suppose. So if I hit the ball or strike the ball at a particular angle with a certain force, then the manner in which the entire system is going to evolve is going to be exactly similar here on the ground as it is going to be, let's suppose, on a moving aeroplane. Which simply means that the laws of mechanics are same here on the ground as it is going to be in a moving vehicle like a train or an aeroplane or whatever it is. Okay? So that means there is no experiment, physically speaking, that can distinguish between two different inertial observers. So we can say that there is no such absolute observer. Laws are valid. In fact, the physical laws are valid for all inertial observers. Now, this is something that retained itself for a long period of time, almost 200-300 years. But then in the 1800s, Maxwell came and combined the laws of electricity and magnetism into what is known as the Maxwell's laws of electromagnetism. Now, one of the greatest predictions of the Maxwell's laws of electromagnetism is the existence of electromagnetic oscillations. Now, what are electromagnetic oscillations? Electromagnetic oscillations are essentially vibrations of electric and magnetic fields, which is what is light. So we know light They are essentially vibrations of electric and magnetic fields traveling through space. Now, till that point in time, we knew waves as something that travels through a medium. So, for example, when you talk about sound waves, they travel through the air. When you talk about vibrations on a string, they travel through the string. When you talk about ripples on the surface of a pond, they travel through the surface of a pond. So one very important question came to mind, everybody's mind, that these electromagnetic oscillations, what is a medium for them? And one hypothesis that has now been disproven is the existence of ether. So it was hypothesized that there is some kind of a ether that permeates throughout the entire universe, with respect to which these electromagnetic oscillations are traveling. And if these electromagnetic oscillations are traveling through that ether, then in fact that ether would represent what we can call as the absolute frame of reference. This was a hypothesis that existed 150 years back. It has till now been disproven. We don't really agree upon it, but because we're looking at the historical development of these ideas, that's why I'm mentioning it. So the Michelson-Morley experiment essentially tried to look at the motion of Earth through this ether. How do they do that? Well, based on Galilean transformation of velocities. So for example, if you have, I'll give you a simple example. If you have, let's suppose, a river, and in that river, the water is flowing from one end to other end at a particular velocity, let's suppose 10 kilometers per hour. And if there is a boat which is traveling through that water with a speed of, let's suppose, 20 kilometers per hour, with respect to the water, then for somebody on the ground, the velocity of the boat will be in the direction of the moving water, 10 plus 20, 30 kilometers per hour. In the opposite direction, it will be 20 minus 10, 10 kilometers per hour. So basically, velocities are going to change in different directions. So what Michelson and Morley did was, if Earth is indeed traveling through this ether, which is supposedly the absolute frame of reference of this universe, then the speed of the light will have different speeds in the direction of the Earth as opposed to in a direction perpendicular to the Earth. And they tried to measure the speed of light in these two perpendicular directions. Without going too much into the details, they actually failed to measure any kind of a relative speed of light in two different directions. Therefore, experimentally, they failed to demonstrate the existence of an ether. Now, after that, of course, Einstein came into the picture. He gave the special theory of relativity, the two postulates. And now we know that the speed of light measured by two different inertial observers is going to be exactly the same in vacuum, irrespective of the relative motion between source and observer. That is, in fact, the second postulate of Einstein. However, at that point in time, when Michelson and Morley's null experiment came into the picture, there were different kinds of scientists who tried to give some kind of a reasonable argument why the Michelson-Morley experiment failed. And one of the hypotheses was given by Lorentz and Fitzgerald, who said that maybe we can explain the null result of the Michelson-Morley experiment, which is the failure of the Michelson-Morley experiment to detect a difference in the speeds of light in two perpendicular directions, by making an assumption that there is some sort of a contraction that is happening to the measuring device in the direction of the moving Earth. Now, for a little while, that hypothesis had some arguments, sounded a little valid, but over a period of time, that hypothesis has been discredited because it doesn't really give us a logically sound theory that we can rely upon to make any kind of a prediction. In fact, the Einstein's two postulates gives a more reasonable and structured formulation of a theory that can predict how things behave, especially when we talk about a relative motion comparable to the speed of light. So that is, yeah. Yes. Exactly. Exactly. Yes. So essentially, what happens is that this is the law of the universe, and don't ask me why the law is the way it is. It is the way it is. Uh, Essentially, what happens is that all inertial observers, whether I am measuring the speed of light, you are measuring the speed of light, somebody traveling at half the speed of light is measuring the speed of light, we will all end up measuring the speed of light in vacuum to be c, which is 3 into 10 to the 8 meters per second. How our measurements are going to differ is that our measurements of length and our measurements of time are going to change, and these quantities are going to optimize in such a manner that the speed comes out to be c. So what is speed? Speed is essentially distance covered per unit time. So if an object goes from point A to point B, so the length between A and B divided by the time it takes essentially is the speed. Now if 10 different observers in relative motion are measuring the speed of light, then they will measure distances and time periods to be different, but the final speed to be the same. So essentially the universe works in such a fashion that the measurements of lengths and measurements of distance will change. It will either be contracted or dilated in such a manner that everybody will end up measuring the speed of light to be exactly the same. Yes. Sure.
Mic check. Yeah, that's better. Right, so this gives, sorry about that. This gives rise to consequences like length contraction and time dilation, and that's what I really want to get into today. Oh, sorry, give me one sec. I have really somehow broken my audio. I think it's a bit too early for me over here. I'm not sure. Give me 1 second. Apologies, guys. I do apologize. Let me just remove the audio input and I'll put a new one.
No issues, no issues.
Okay. Mic check 1 2. Yeah, that's better. You can hear me still, Mr. Das?
Yes, I can hear you.
There we go. Fixed. Apologize, guys. My settings seem to have got a bit mixed up there. It shouldn't be clipping and everything should be sorted now. Okay, right. So length contraction. Length contraction can be confusing because it seems counterintuitive. It doesn't seem to make sense if you when someone explains it to you. Your video that you did about the train and the mirror with light being shined backwards and forwards was the best explanation that I'd seen and helped me understand it. So could you give us a basic explanation of how to understand what length contraction is?
Yeah, would you like me to share the screen?
Yes, yeah, that would probably be the best thing. Yeah, apologies again, guys, for the audio issues there. I don't know why that happened. But yeah, so we're going to talk about length contraction now and how to actually understand it. So let me get Mr. Das's screen up.
Can you see my screen?
Yes. Now, let me just put you on to present. Okay, over to you.
Shall I start explaining?
Yes, please.
Yeah, I thought that instead of just talking, because when we talk, there's a lot of words that might get confusing because this is a very technical subject, I would use a little bit of a visualization and an example. So you can ignore the calculations if you're not interested in the calculations, but try to understand what's happening. So what I've taken here is that I've taken 3 spaceship or rocket ships, you can say. Okay, I have 3 different rocket ships and the Earth is here. So with respect to the Earth, I'm giving the rocket ship some kind of a velocity. So you can assume that there is 3 rocket ships that are traveling outwards from the Earth in the same direction. Now the first rocket ship has the pilot or the observer. I'm going to call it as A. The second rocket ship has this pilot or the observer. I'm going to call it as B. The third rocket ship has this pilot or the observer that I'm going to call as C. Now the proper length of each of this rocket ship is 1 meter. It's a hypothetical example, right? So I can give it any kind of a value. Now what is proper length? So in relativity, I saw that there was a lot of confusion regarding what's real and what's apparent. So we don't really, when we talk about relativity, when we teach it in a university classroom, the word that we use is not real or apparent. We use what is known as proper length or proper time, or rest length or rest time, or relativistic length or relativistic time. So what proper length means is, if you measure the dimensions of an object in the rest frame of that object, that's a proper length. So for example, you can look at the chart here. I've calculated this chart based on my calculations. So you can ignore the calculations, they're perfectly fine. You can look at this chart. So in this chart, I have this x-axis, which is the length of A, B, and C. So A, B, and C are the rocket ships. And in the y-axis, I have with respect to some observer. So in relativity, when we talk about length or time or any other physical quantity, we always have to specify with respect to some observer, right? As I just now told you, that there is no absolute frame of reference. All kinds of measurements depend upon some relative observer, right? So with respect to an observer, the dimensions of an object might be different compared to with respect to another observer. So let me define these observers. A, B, and C, these are observers. So let's suppose that A is at rest, right? V is equal to 0, it's at rest here with respect to the Earth. B is traveling at 80% the speed of light, the forward direction. And C is traveling at 90% the speed of light in the forward direction. So what's going to happen if A measures the length of its own rocket? Okay, so if A measures the length of its own rocket, it is going to end up measuring what is known as the proper length, which is 1 meter. That is what I've defined here. Okay, if A measures the length of its own rocket, it ends up measuring 1 meter, which is a proper length. Similarly, if B measures the length of its own rocket, it measures 1 meter, same. If C measures the length of its own rocket, it ends up measuring 1 meter. So as you can see here, no matter what happens, no matter what velocity you're traveling or speed you're traveling with respect to somebody else, if you measure an object in your frame of reference, you will end up measuring its proper length or proper dimensions. No differences there. The problem happens, or the change happens, when you try to measure another object which is traveling relative to you. So if you're trying to measure the dimensions of a rocket traveling relative to you at a certain velocity, then you will end up measuring some value which is different from if you would have measured the same value with respect to the rocket being at rest. So for example, let's suppose that A tries to measure the length of rocket B. Okay, so if A tries to measure the length of rocket B, what is he going to end up measuring? See, rocket B has a length of 1 meter with respect to B. But what is the length of the rocket B with respect to A? I hope that this is not getting too technical, just hang with me. So the length of B with respect to an observer A depends upon the relative velocity. So what is the relative velocity? The relative velocity is 80% the speed of light. And the moment there is a relative velocity, he ends up measuring, A ends up measuring that B has a length of 6.6 meters. You see that? The proper length is 1 meter. The proper length is 1 meter. But if A tries to measure the speed of B, because B is traveling at 80% the speed of light, A will see that the length of B is 0.6 meters. Similarly, the reverse is also true. That means if B tries to measure the length of A, he will see that the length of A is 0.6 meters. Right. Similarly, I have another example here. See, if A tries to measure the length of C here, now because the relative velocity is 90% the speed of light, he will see further contraction. So if A tries to measure the length of C, he will see that the length of the rocket ship is 0.43 meters. Similarly, if C tries to measure the length of A, he will see that the speed of the rocket is 0.43 meters. So as you can see, the speed of any kind of the length of any kind of a object, I have taken the example of a spaceship or a rocket here, depends upon the relative velocity of the observer with respect to the object. So as long as the object is traveling at very high speeds, the greater speed it is at, the observer will measure the length to be contracted compared to if B itself was measuring its own length, or C itself was measuring its own length. I have further gone in a little bit more detail to calculate what B will measure for C and C will measure for B. It's a similar thing. Their relative velocities are also different. So based on that, they will also experience some sort of a length contraction. So as you can see, the final crux of the matter is this. If I try to measure the length of an object which is at rest in my frame of reference, I will measure its proper length. But if that object starts traveling at a velocity with respect to me, then based on that relative velocity, my measurements of its length are going to be contracted in nature. It doesn't necessarily mean that the person who is in that spaceship, so if I'm A and there's a person who is in spaceship B, that same person who is in spaceship B will not experience any contraction, but according to my calculations, the dimensions of that object will have appeared contracted. So essentially, in relativity, everything is relative. Measurements of distances, measurements of time, everything is relative with respect to an observer who is in relative motion. So that is the crux of this whole thing.
That I was kind of mouthing in the background there about how brilliant that explanation is. The table that is, it's so simple. There's no way to not understand what that table is saying. So what it shows here with what you've described is that the frame that you're in doesn't have contraction, because if you're in that frame, you don't have any motion. You're relative to yourself, you're stationary. So
yes.
If we're comparing that to the Michelson-Morley experiment, whereas Lorentz would say that the fact that the Earth is in motion causes this physical contraction, what Einstein would say is that you would only be able to see the contraction of Earth's motion relative to the Sun if you were on the Sun and that was your rest frame. Yes. And conversely, if you were on the Earth, then you would see the Sun contract the same amount that the Sun would see the Earth contract. So each person, if there was a person on the Earth or a person on the Sun, they would experience different things.
Yes, and they would be very much right according to their perspective.
Yeah, brilliant. And then the fact that you've added in a third frame on yours is one of the most important things in this argument, because it shows that the contraction is not happening in what would be considered the rest frame. It's purely what you experience if you were to be able to measure the thing that had a relative velocity moving away from you. That's the only way that you would experience contraction, is if you were trying to measure the frame that was in motion relative to you.
Yeah.
Brilliant.
Can I explain how the Lorentz deformation hypothesis came into the picture?
Yes, please do.
I'll stop the screen share.
Yes.
Okay, so essentially what happens in science is that sometimes if a new experiment comes into the picture and disproves a previously valid theory, then all the scientists want to explain why that's happened. That is how science progresses. If you have some sort of a valid theory, it must be able to predict everything. If it fails in some sort of an experiment, that we need to come up with an explanation why it failed. So when the Michelson-Morley experiment failed, then of course there were different kinds of scientists who wanted to explain why it failed, and one of the explanation was given by Lorentz, in which he suggested that maybe the interferometer in the direction of motion of the Earth has experienced some kind of a contraction or change in its shape, so that we can account for the null result. Now, of course, today we do not accept that hypothesis, but a valid question may arise that why is it not valid hypothesis, right? It could be a valid question that why is that hypothesis wrong? So I want to give an answer to that question, that why that hypothesis is wrong. So let me go back to my original discussion when I started with the principle of relativity. You remember I said that
yes,
you cannot distinguish between two inertial frames of reference based on physical experiments. There is no physical experiment that can distinguish between two frames of reference that are in relative motion as long as they are inertial frames of reference. That means essentially there is no absolute frame of reference in the universe, and this was true for mechanical laws. But then when other domains of physics started developing, so for example, when electromagnetism came into the picture, then people asked the same question, that is there any kind of an electromagnetic experiment that can distinguish between two inertial frames of reference? So for example, if I give you a very simple example, if I have like a wire, a coil of wire, and I move it relative to a magnet. So if I have, let's suppose, two magnets, a north pole and a south pole, and I move a coil of wire through that magnetic field with a certain velocity, then a EMF is going to be induced in that particular wire. So that basically a current is going to flow through that wire. This is purely a result of electromagnetic behavior. Now, it doesn't really matter whether you move the coil and keep the magnets at rest, or whether you keep the coil at rest or move the magnets, both of them are going to generate the same kind of current. So essentially what happens is that there is no experiment in electromagnetism that can also distinguish between two inertial frames of reference. So for example, if I'm in the ground and if I have a team of scientists traveling through an aeroplane smoothly at very high speeds, they cannot perform an experiment that suggests that that frame of reference is more special compared to my frame of reference. So essentially there is no special frame of reference in the universe. Everybody has a valid frame of reference, and with respect to everybody's frame of reference, the physical laws are completely uniform, completely same, completely valid. Now the problem, yeah.
Sorry, I didn't mean to interrupt there. So that would be why Einstein said that he didn't think there was any optical experiment that could detect the Earth's motion.
No. So optical would essentially mean electromagnetic oscillations, right? So that means there is no frame of reference that gives any special preference to electromagnetic experiments. So this is, in the physics terms, it is said that the Maxwell's laws of electromagnetism are invariant when you go from one inertial frame of reference to another. That means all inertial frames of reference are equal when it comes to not just laws of mechanics, but also laws of electromagnetism. And when I say electromagnetism, I am basically talking about electromagnetic behavior. So now the problem with the Lorentz deformation hypothesis, which was initially given, it sounded reasonably fine to account for the the Michelson-Morley experiment. But the problem with that deformation hypothesis is that if we accept that the Lorentz deformation hypothesis is true, then we have to also accept that there is a special frame of reference in our universe, which is the ether frame of reference, with respect to which all other inertial frames of reference are in relative motion. That means in that very instant we will have an absolute frame of reference, and we will need new physics that will basically essentially have a set of laws for the absolute frame of reference, and the moment we go from the absolute frame of reference to other relative motion or relative observer's frame of reference, we need to make some corrections. Unfortunately, that has never really happened. There is no such experiment, either mechanical or electromagnetic, that can distinguish between various inertial frames of reference or various observers. There is no experimental evidence like that. So if we accept the Lorentz hypothesis, we'll have to accept that there is in fact some kind of a absolute frame of reference with respect to which the interferometer was moving, and somehow the interferometer's deformation was the result of that relative motion with the absolute frame of reference. But unfortunately, we do not have any kind of a physical experiment to demonstrate that any such absolute frame of reference exists. So we can't really accept that idea. Further, there are other kinds of arguments also, that if there was indeed some sort of a deformation in the experimental setup, it has to be explained by the atomic structures and the intermolecular forces and how they sort of create the necessary contraction. But we don't have any kind of a consistent theory that can explain why any kind of a contraction would take place, would happen in the first place. So essentially, it's okay to give a hypothesis, but it's not really backed by any kind of an experimental data, or it's not created any consistent physical theory in the first place. On the other hand, when we look at Einstein's postulate, Einstein's postulates creates a very complete framework of a theory that can be used to explain why things are the way they are.
Right. So Lorentz had his idea of contraction, and for him that was an explanation of why they didn't get the fringe shift that would have been detected from the different directions of light. Now, Einstein also has his version of length contraction. What is the relationship between what Lorentz came up with for contraction with how Einstein describes it, and how do they differ?
Well, the Lorentz contraction essentially says that the Michelson-Morley interferometer experimental setup might have experienced contraction as Earth was going around the sun at a
An actual
particular
physical
velocity.
contraction of all the molecules and everything.
With respect to the lab, with respect
Yeah.
to the scientists present in the lab.
Right.
But as I just now demonstrated in my earlier chart, according to Einstein, the observer A measures the length of his own rocket to be the same. It is the other observer B or C, which is in relative motion, who measures the length to be contracted. Right. So the contraction is only seen for another object that is in relative motion. It is never seen for the very object which is at rest with respect to you. So that is not the contraction that Einstein is talking about.
No. So Einstein would say that it's not that you're contracting and you just can't measure it because your device is also contracting as well. Einstein's explanation is that the lab frame, there's no contraction in the lab frame. The contraction would exist in the thing that is moving relative to the lab frame.
Yeah, contraction is essentially the measurement of an observer of another object that is in relative motion. So if there are multiple observers who are measuring another moving object, based on their relative motion, they will measure a different kind of contraction. So as I showed in the earlier chart, B and C will measure different contraction of A because their relative velocities are different.
Brilliant. I'm just trying to formulate the questions in my head correctly. Okay, so the next question would be, a lot of the confusion comes to, is the contraction real? And it's a confusing question. How would we show that this contraction exists in the real world? What would you say is the best experimental evidence to show that this contraction is not just a mathematical thing, but is something that can affect the reality that we're in?
Okay, so let me focus on the first part of the question first. What does it mean? Is it real? See, when we talk about physics, we'll have to get a little bit into the nitty-gritties. So as you might have noticed, I'm always talking about with respect to another observer, right? So I have many students in my class who also ask me, sir, is this real? Is this really happening? Or is this an optical illusion? And that is a very valid question. I understand where they're coming from. But we need to understand that in relativity, measurements are relative. Everybody who is making a set of measurements may have different measurements based on what is their relative motion with respect to the observer. So with respect to the observer is very, very important. So for example, if something is traveling with respect to me, then I might measure that object that it might have contracted, but for that object, I might have contracted, right? So essentially, there is a sort of so for example, let's suppose there are two rocket ships traveling opposite to each other. Let's suppose, then according to the rocket ship A, the B rocket ship will experience contraction, and according to rocket ship B, the A rocket ship will experience contraction. So it's real, but with respect to the observer who is making the measurements and calculations. There is no contraction with respect to the observer in the rest frame of the object, first. Second, there are different kinds of experiments, as you yourself mentioned in the beginning of the video. There is a very famous Muon experiment, Muon decay experiment. Essentially what happens is that muons are subatomic particles that are created on the top of the atmosphere when cosmic rays from outside the Earth come and strike the atmospheric gas molecules. So these muons are these subatomic particles that only live for a very fraction of a second, and they usually decay into further smaller particles over a period of time. Now, if you measure the speed of the muon as it is coming from the top of the atmosphere to the sea level, and if you measure the what do we call as the lifetime of a muon particle, because it's a radioactive particle, it decays within a small fraction of a second, then it is usually found that it should not be able to reach the sea level. It should decay somewhere in the middle. But what is actually found in the experiment was that a large number of muons actually travel and reach the sea level, which is not possible in a non-relativistic setup. So what is essentially happening is, we can look at this experiment from two different perspectives. We can look at it from the perspective of a scientist on the ground, or we can look at it from the perspective of the muon himself. Let's first look at it from the scientist on the ground. So when we look at scientists on the ground, he is observing a muon. The muon is traveling at a particular speed. What is essentially happening, according to relativity, is that the clocks of the muon and the clocks of the scientist are, you can say, they are going at different rates. So this brings us to what is known as time dilation. That means if an object is traveling at a particular sort of a velocity with respect to me, then the rate at which the watch ticks is different from the rate at which the watch ticks for me. So if a muon is at a rest frame of reference, so if I have a muon which is at rest in the lab frame, it has a particular lifetime which is not the same as the lifetime of the muon if it is traveling at a particular velocity. So if it is traveling at a particular velocity, because its clock ticks slower, so its lifetime increases. So because its lifetime increases, therefore it has more time to come and reach the sea level. And the rate of decay and the number of particles that were found at different levels performed by the various scientists actually proved that the time dilation formula is correct. So this is the validity of the time dilation formula. But what about length contraction? Well, if we make the measurements not with respect to the scientist on the ground, but with respect to the muon, then the picture is very different. So if the muon is coming from the top of the atmosphere towards the ground, and we think from the perspective of the muon, so imagine the muon is a person and he is traveling at the speed of the muon and he is looking down at Earth. So what is going to happen for him? Because for him, the clock is ticking at its proper time interval, right? So what is happening for him is that the Earth's atmosphere appears contracted. Okay, so the muon exists for the same lifespan that it would exist in a laboratory frame of reference, but the Earth's atmosphere appears contracted. So therefore, he has to travel a shorter distance compared to what we in the ground frame would think the muon was traveling in the first place. So that is the validity of the length contraction argument. So as you can see, time dilation and length contraction really depends upon from which observer's perspective we are making these observations, but both of them are valid equally and they have been experimentally corroborated.
So it explains something like the classic twin paradox. You've got two twins, one's on Earth, one's on a rocket ship traveling away from Earth at relativistic speeds. The time for if you were to be on Earth and measure the time on the rocket ship, it would be ticking slower than the clock on Earth. So the person in the rocket ship relative to the person on Earth would age slower. But there's also a symmetry, right? So for the person on the rocket ship, the clock on Earth would be ticking slower. So yes. How do we go about rectifying that? What if the ship stops traveling and then turns around and comes back towards Earth? What is going to be the experience of each of the twins in that circumstance?
So if we just look at half the journey, let's not look at the full journey first. To answer your first question, are both of them equally correct? The answer is both of them are equally correct. With respect to somebody on Earth, the twin will age, like it will be younger. But with respect to the twin who is traveling, I would probably be younger. Both our calculations are equally valid for both the observers, right? Now the paradox comes into existence when we look at the motion when she returns back. Now that's a little bit of a complicated motion because special theory of relativity is called special because the word special is referring to inertial frames of reference. The special theory of relativity as a subject only deals with inertial frames of reference. Inertial means, in a very simple layman word, moving at constant velocity. It doesn't deal with phenomena that is accelerating upwards or downwards. So when you have a rocket that goes and comes back, there is a moment of deceleration and acceleration that is happening. Usually acceleration, deceleration, that is taken care of by general theory of relativity. But special theory of relativity itself doesn't deal with accelerations and decelerations. And also when we look at the twin paradox, it is only, there are some kind of assumptions that we make about the nature of simultaneous events that lead to this kind of a paradox. But when you look at space-time diagrams, this problem has been performed geometrically speaking using space-time diagrams, and it isn't really a paradox. It usually gets resolved when the relativity is applied properly in a proper setting. So it's only a paradox because when we try to look at it from the perspective of Lorentz transformations, but the moment we shift from Lorentz transformation to space-time diagrams or Minkowski space-time diagrams, in the context of relativity, it gets easily resolved.
And you
And
do
also,
have an excellent video on Minkowski space-time diagrams. If any of my mods are able to find the Minkowski space-time diagram video by For the Love of Physics and put it in the chat, I'd appreciate that. Thank you.
Yeah.
So I'm still trying to get over your explanation with the chart. That's one of the simplest ways of visualizing it I've ever seen. And I think it answers a lot of the questions that have been answered. So one question that has been asked in the chat is, could you clarify on what you mean when you talk about the muons on appears versus really?
Yeah, I can see that this words creates confusion because in layman language, when we mean appears, we feel that it has something to do with some illusion, like an optical illusion or something like that. Mm-hmm. When we say real, I mean that's what's actually happening, right? But in relativity, we don't really use the words appears or real. Instead, we use the words proper length, proper time, or we use rest length, rest time, rest mass. This is because in relativity, every observer's observations are equally valid. There is no observer whose observations are more valid than somebody else's observations. Every observer in the universe, however infinite observers are there, all of their observations are valid from their perspective. The only special case is made for the rest observer. So for example, if I have a clock and I'm looking at how the clock ticks and the clock is at rest with respect to me, then the rate at which the clock ticks, the time interval will be called proper time. If I take a rod and I'll measure the length of the rod, then that would be called proper length. So essentially, if the clock or the rod is at rest with respect to me, who is making the measurements, then its length and its time period is called proper length or proper time. But if the rod starts traveling at a particular velocity, then it has a relativistic length, which is equally valid for me, but it is different from its proper length. And if the clock starts traveling at a particular velocity with respect to me, the time period of its ticking is going to be relativistic time period given by the time dilation formula, but it is equally valid for me. So even though the relativistic lengths or relativistic time periods might be different from the proper length and the proper time periods, but they're equally valid for those observers who are making those measurements in the first place. It has nothing to do with any kind of an optical illusion or anything like that. It is purely because everything in physics is about measurement. We have to measure everything, whether it is mass, whether it's length, whether it's energy, whether it's any kind of physical quantity, we need to measure it. But what relativity brings into the picture is that every measurement is related to an observer who is making those measurements, and for that observer, his measurements are perfectly valid. Sometimes some people may say real, but what they essentially mean by real is proper. That means proper means with respect to rest frame of reference of that clock or the rod.
And this is something that I've tried to get across. The thing is with language, with spoken words, is that it's messy and inaccurate. And I think the best way to understand these concepts is by looking into the maths, because relativity is a mathematical framework. It's all explained in the maths, and there's different languages, there's different ways of saying things, and it can be hard when you're trying to use an inaccurate method like spoken language to describe something mathematical. And I understand why there's confusion. Would you agree with that?
Yes, I definitely agree, because when I take my classes, I have a lot of students who are studying this subject for the first time. Even they ask similar questions that, sir, is it really happening or is it an optical illusion? Well, the truth is it is really happening, but only with respect to that observer. So only with respect to that observer, it's really happening. But with respect to some other observer, some other phenomena is happening. A different length contraction, a different time dilation is happening, but it's very much real for that particular observer. So when we come into relativity, when we study relativity as a physics student, we have to be very careful that the measurements that we are making, the calculations that we are making, we are only doing that from some perspective or some observer. So if you remember the chart that I made some time back, I have written that the length of A with respect to B or C. right?
Yes.
So there is no absolute length of A. There is a length of A with respect to A. There is a length of A with respect to B. There is a length of A with respect to C. So based on which observer is making the measurement, length could be very different. But it is very much real for those observers.
And the only way to get the proper length is to have the length of A with respect to A, or the length of B with respect to B. That's the only time that there's a proper length. So
exactly.
This is why I got you on. I knew you'd be able to break this down so well, Mr. Das. Thank you so much.
Thank you. Thank you so much.
So there is one other thing that people people are arguing this have been throwing around, and that's a particular quote from an article that is talking about something slightly different to length contraction. The quote is that the idea that objects contract in length when they travel near the speed of light is a widely accepted consequence of Einstein's special relativity. But if you could observe such an object, it wouldn't look shorter at all. And that's when they stop their quote. But when you read the rest of the article, it's actually talking about a phenomenon called terral rotation, with how the difference between the time of measurement and what you would see, and how instead of seeing it being contracted, it would appear slightly rotated. Do you have anything that you know about that understanding of the way to look at relativity and what you would view?
Could you repeat the statement? I couldn't catch it.
Terral rotation. So it's talking about how when you view an object that is traveling away from you, it's often called the Terral effect, and it's named after James Terral, a physicist at Los Alamos National Laboratory. The apparent rotation of an object moving near the speed of light is in essence a consequence of the time it takes light rays to travel from various points on the moving body to an observer's eyes. So when you were to view an object that was moving away from you at relativistic speeds, even if you could measure it, what you would see you would see a rotation rather than a contraction.
Okay. So essentially what happens is that when we talk about relativity, we talk about very simplistic scenarios because the concept itself is so difficult to understand that it's better to have an understanding of simpler examples first. So the length contraction happens in the direction of motion. It doesn't happen in a direction perpendicular to motion. So when we teach subject of relativity, we usually take the example of a rod or a scale, because a rod or a scale is a one-dimensional object that travels along a particular direction. It's easy for us to see the contraction. But in our day-to-day life, we don't really deal with one-dimensional objects. We deal with three-dimensional objects, objects that have shape, objects that have structure, right? So essentially what happens is that let's suppose that I have, let me take this object, right? So essentially think of this as a rod, okay? If it was, instead of traveling in this manner, what if it was traveling in this particular manner, right? Now this is not a very difficult problem. I usually do it in my class. Not only there is some kind of a contraction that happens in the direction of motion, there is also some sort of a change in its orientation that happens. Okay, we can easily calculate it based on relativistic assumptions. So in a very simple example like this, when the rod is traveling not exactly in a linear fashion or longitudinal fashion, but in an inclined manner, the nature of inclination changes. Okay, so when you take this argument forward to rigid bodies or three-dimensional objects, then of course there is a little bit of a change in the structure, a smearing of the sort of object happens. I think that is what it is talking about. But then that also is the result of relativity when you look at the general picture, not just in the direction of motion, but you make the further calculations, because the equations are very complicated. But if you make the calculations along all three different axes, what is the nature of contraction that happens and what does the final object look like, I'm very sure that it is not just a pure contraction. There is also a little bit of a rotation and smearing that ends up happening. In fact, if you look at Wikipedia, they have a couple of images for that kind of an object also. So volumetric contraction also happens. Yes.
Yeah, the images of a dice moving away from your relativistic speed, how because it's a three-dimensional solid object, it would have, like you said, parts of it are inclined relative to the observer. So as you were trying to observe it, parts of it would appear rotated, and you could almost see behind the disc, behind the die. So thank you. So it's more to do with the fact that when you talk about length contraction in general, you talk about, like you said, a one-dimensional object traveling away, but that's not what the universe is. The universe is three-dimensional. Objects are three-dimensional. So there's going to be more than kind of one calculation to take into account.
Yes, we usually talk about one-dimensional objects because it's simpler to explain to students. It's simpler to understand for somebody who is a beginner. But when you talk about three-dimensional objects, then there are three different equations that will come into the picture: Lx, x-axis; Ly, y-axis; Lz, z-axis. Then the final calculations will depend upon a very complicated set of equations. But we restrict our discussions mostly to one-dimensional motion along the x-axis, just to simplify the concept, because anyways the concept is already very complicated to understand.
It is. It is a very complicated concept, and I think you have actually cleared up a lot of it for us today, Mr. Das, and I very much appreciate you taking the time. I know it's very late for you over there. Must be coming up to 1 o'clock now for you, hey, in the morning.
Yes, it's 1 o'clock. Yeah.
So I'm going to let you go, and I'm going to say thank you so much for your time. I really do appreciate it. And guys, if you would like to see more of Mr. Das's work, please head to the channel linked in the title, For the Love of Physics. You've got hundreds of videos over there, right? Hundreds.
Yeah, but not enough, I think, because I would like to contribute more to these kind of discussions. It really makes me very, very happy. See, I'm essentially a teacher, and the reason I'm a teacher is because I find a lot of fulfillment in the process of teaching. I love physics, that's why I've named the channel For the Love of Physics. And I also love teaching. So these kind of discussions, when we discuss different concepts of physics, and where I myself learn something and I'm able to help somebody else gain a little bit of clarity about this beautiful subject of physics, it really gives me a deep sense of fulfillment. So I also want to thank you, Craig, for inviting me to this very beautiful and wonderful
My pleasure.
discussion.
Absolutely my pleasure, Mr. Das. I honestly thank you so much for taking the time. Please, guys, please go and check out Mr. Das. And Mr. Das, I will speak to you soon. I'm sure I'll have more questions for you in due time. Thank you. Have a nice day.
Thank you. Thank you so much. Have a nice day.
Goodbye.
Bye.
Well, guys, wasn't that absolutely fascinating? Yeah, Whitsit's wrong. You know, I very much like Mr. Dash just said there. I like teaching. I like people to learn from me. Yeah, I love shouting at flat earthers that are idiots and stuff. But you know, my goal is to teach people so that they can understand more. And Whitsit is one of those people that has the ability to take people in with his incessant narcissistic droning that makes him seem like he's right, but he's not. I think Mr. Das there touched on every one of Whitsit's relativity misunderstandings, and the only way now that Whitsit can say that he's right is if he disagrees with the actual experts in the subjects. So, you know, he knows more than the people that teach these subjects. That's the only thing that's left over now. So, I know this was a different kind of stream to normal. You know, I know that probably not as many people would want to watch this as the dumpster fires that I do, but I am going to be doing a lot more kind of science communication content, and I really do hope you enjoyed this and continue to support the channel. If you want to see more of this kind of thing, please, if you're not already, go and sub to For the Love of Physics. I can watch a channel for hours. It's absolutely fascinating. He's such a good teacher. We've got Roy Liu, who became a new member. Welcome to Scrappers. And we got Turing Test 2 for £3, who says, "Wake up, FTFE, you're muted." Yeah. So here's my keyboard. It's not attached to anything. And I dropped it on the floor, and it opened up about 4 new audio inputs when I did that. And I couldn't figure out which of the audio inputs were the ones that were feeding back on each other. So I'm sorry about the little audio mishap there. Vicari Vision for $4.99 says, "Thanks, FTFE. I know I learned a lot from your guest, and I've learned so much from you." Thank you very much. That is what I'd like to do. I see someone in the chat who's called Fox Official, who used to be a flat earther, and I'm going to get him on at some point and have a chat with him and have a laugh about the things that he used to say. But in the meantime, I hope you've enjoyed this different discussion on the nature of our world. Whitsit, get it up here, you moron. Try and argue with me now, I dare you. No, I know you will. You're going to take everything that was said here and misunderstand it because, you know, you're barely a talking chimp. But pat in the chat for $2, get more edumacated today. Here's the tuition. Thank you very much. I will see you guys soon. I was going to release a debate short today, but this came up instead, so we've released this. So the debate short will probably be out tomorrow. We'll follow in very soon with a new episode of Flerfs are Idiots, or an old episode of Flerfs are Idiots. A remake, possibly. We'll see what's going on. But thank you. I will see you soon. And remember, stupidity is not a right. Fight the flat earth. Fight the flat. Fight the flat.